Hi, this is a video to help you through the activity on attractive forces and solubility. On your activity, there is a table of the 5 different attractive forces between molecules. They are listed in this table from the strongest on the top to the weakest on the bottom. On the table is a cartoon representation for each of the attractive forces, followed by 2 examples of each. Please take some time now, examine this table, and answer as many of the questions that follow before you go on. I'll now give a brief description of each of the types of forces. Ionic forces are the strongest force between 2 molecules, or between 2 ions, really. It's always between an ion that has a full positive charge and an ion that has a full negative charge. In my first example, I'm showing a positive sodium ion attracted to a negative chloride ion. These 2 things are separate ions, and the sodium, having a positive charge, is attracted to the chlorine with a negative charge. Here's another example. In this example, each molecule has a positive and a negative charge within it. This is a special type of ion called a Zwitter ion, where there's a positive and a negative charge on the same molecule. An ionic interaction, in this case, is shown here between the part of one molecule that has a negative charge and the part of the other molecule that has the positive charge. In order for an ionic interaction to happen, you must have both a positive and negative ion present. An ion dipole is a new type of interaction that we haven't seen before. You take either a positive or a negative ion interacting with a dipole. So in this case, you could have either a positive or a negative, and therefore it would interact with the dipole of the opposite partial charge. Here's an example. Here I have a sodium ion, which is a positively charged ion, interacting with the partial negative charge on a polar water molecule. This is different from the ion-ion interaction in the fact that the ion-ion is a full positive interacting with a full negative ion. In this case, we have a full positive interacting with a partial negative. So this is a full partial interaction. Here's another example. In this example, the molecule itself is a negatively charged ion. There's a negative charge on the oxygen. There are also polar bonds in this molecule, and so the carbon here is partially positive. The ion-dipole interaction between the 2 molecules is shown as the negatively charged oxygen being attracted to the partial positive charge on the carbon. The ion-dipole interaction is kind of a mixture between an ionic interaction and a dipole-dipole. It's a mixed interaction where instead of having partial-partial or full-full, you have a partial-full interaction. We saw hydrogen bonding in a previous activity. This is a type of strong interaction between a lone pair on one atom and the partially positive hydrogen on another atom. It is not quite a covalent bond, but it is a very strong interaction that's nearly as strong as a bond. It's very strong, but it's still not as strong as an ion-dipole or an ionic interaction. Dipole-dipole is just when 2 polar molecules are interacting through attractive forces between their partial positive and partial negative poles. Here are 2 examples. Here the partial negative charge on the oxygen is interacting with the partial positive carbon along this polar bond in each molecule. And here's another example. London forces are different than dipole-dipole interactions because London forces are not permanent dipoles. They're induced or temporary dipoles. The dipole moment in a polar molecule is permanent, and this is temporary. The interaction for London forces through temporary dipoles is much weaker than the interaction between permanent dipoles. All molecules have London forces, and London forces are only important when other forces are not present. London forces are going to be most significant for nonpolar molecules. Here are 2 examples of nonpolar molecules which can interact with each other through London forces. Nonpolar molecules will only have London forces. If a molecule is polar, it will have London and dipole-dipole, but the dipole-dipole interaction will be stronger and more important than the London forces. A polar molecule may also have hydrogen bonding, and if that's the case, the molecule would have hydrogen bonding, dipole-dipole, and London. but the hydrogen bonding would be most important. Ionic compounds can either have ion dipole or ionic interactions, depending on what charges are present. If only a positive or only a negative charge exists, it can interact with other molecules through ion dipole. However, if both positive and negative charges exist, an ionic interaction will be the most important. Let's apply this to the 4 molecules in the table below. In this problem, I'm asking you to look at these 4 molecules and determine what forces are present between them. Unless I specify otherwise, when I ask you to tell me what forces are available in these molecules, I'm talking about the forces between 2 identical molecules. So the forces between 2 molecules of carbon tetrachloride, 2 molecules of water, 2 molecules of chloroform, or 2 molecules of this acetate ion. The first thing you'll want to do is characterize these molecules as polar or nonpolar. If they are polar, it's important to check to see if they can hydrogen bond or if they have ionic charges as well, because those 2 things, hydrogen bonding and ionic charges, lead to a special type of interaction. Let's go ahead and characterize these. Now I'm going to draw the Lewis structure of these molecules so that we can decide whether they're polar or nonpolar, and whether they have hydrogen bonding or ionic charges. Here's the Lewis structure of the first molecule. This is carbon tetrachloride. This molecule has polar bonds. However, it's overall nonpolar because all of the polar bond vectors cancel each other out. So this is a nonpolar molecule. This is the Lewis structure for water. Once again, we have polar bonds, this time between hydrogen and oxygen. These 2 dipole moment arrows do not cancel one another out because the molecular geometry around oxygen is bent. There's an overall dipole moment towards the oxygen and away from the hydrogens. This molecule is polar and is also capable of hydrogen bonding. In the third example, we essentially are replacing one of the chlorines on carbon tetrachloride with a hydrogen. All of the carbon-chlorine bonds are polar, but the hydrogen-carbon bond is not polar. And so now, all of the bond dipole moments do not cancel each other out. In fact, they add to give you a molecular dipole moment. This molecule is polar. Ask yourself if it can hydrogen bond. This hydrogen here is not partially positive, because it is not part of a polar bond. If a hydrogen is partially positive, it must be part of a polar bond, but that hydrogen is not positive. This molecule does have lone pairs, and so it might be able to hydrogen bond with another type of molecule, like a water, but it does not contain both components that are necessary for hydrogen bonding with another molecule of itself. So this one is just polar. Now let's draw the Lewis structure of the last example. Use the structural formula to help you. The structural formula tells you that there's a carbon with 3 hydrogens attached, followed by another carbon that has 2 oxygens attached. To make this Lewis structure complete, I have to have 4 bonds to carbon and 2 bonds to each of the oxygens. So one thing I can do is to erase the 2 lone electrons and make it into a new bond between carbon and oxygen. Now my carbon has 4 bonds, but I don't have 2 bonds to this oxygen I've written on the top. That's okay. There's a negative charge on this structure, and that means that I've added an extra electron. Now my octets are full. This particular oxygen is violating one of the common bonding schemes, but that can be expected because you have a negative charge on this molecule. In fact, the negative charge is on the oxygen that possesses an extra electron. Now we can see that this molecule is polar. It has 2 polar bonds, and so its overall molecular dipole moment arrow looks like that. So this is a polar molecule, but one important thing about this molecule is the ionic charge. It's both polar and ionic. It's important to notice this because ionic charges bring you up to the ion-dipole or ionic interactions. Now let's fill in the table. London forces are present in everything, so I'll check off that box for every one of the molecules. The dipole-dipole interactions are in molecules that are polar, but not part of molecules that are nonpolar. So all polar molecules will have dipole-dipole interactions. The only molecule that has hydrogen bonding is water, because it is the only molecule that possesses both lone pairs and partially positive hydrogens. Ion-dipole interactions require an ion and a polar molecule. The last option here is both polar and ionic, and so it is capable of ion-dipole. Ionic interactions require both a positive and a negative ion. Even though we have a negative ion in one of these examples, there is no positive ion to be its match, so there are no ionic interactions in the molecules shown in this table. Now let's move on to the next question and draw the hydrogen bonding networks in ammonia. Hopefully you can see that there are 3 different polar bonds in this molecule. That leaves a partial negative charge on nitrogen and a partial positive charge on each of the hydrogens. I could also show this by writing dipole moment arrows along each of the bonds from the hydrogen towards the nitrogen. Now let's draw a hydrogen bonding interaction with another molecule of ammonia. In this case, I'll draw a hydrogen bond between the lone pair on my pink nitrogen and a partial positive hydrogen on another molecule. Now I'll do the same but opposite for the partial positive hydrogens on the pink molecule. I'll draw 3 other molecules of ammonia with their lone pair pointed towards the nitrogens, so it's easy for me to draw the hydrogen bonding interaction. The hydrogen bonding interactions are from the lone pairs on each of the nitrogens to one of the partially positive hydrogens. Each molecule of ammonia can make 4 hydrogen bonding interactions, and this network would expand infinitely in a solution of ammonia. Let's talk about solubility. You know the term like dissolves like, and that's usually used to refer to solubility. The term like dissolves like means that things that have like characteristics as far as polarity goes will dissolve other things that have similar properties. In other words, polar substances will dissolve in other polar substances, and nonpolar substances will dissolve in other nonpolar substances, but polar things will not dissolve in nonpolar things. The molecule in front of you is a polar molecule. The carbon-oxygen bond is polarized because oxygen is more electronegative than carbon. I can show this with partial charge symbols or with a dipole moment arrow. I'm going to be specifically talking about solubility in water for the rest of this activity. Water is a polar molecule, and this molecule, which is acetone, is also polar. And therefore, water can interact with this molecule, and it will be attracted to this molecule through opposite polarities. There are 2 main interactions that water has with a molecule like this. Ask yourself whether this molecule could hydrogen bond with other molecules like it. The answer is no, because this molecule contains lone pairs, but it does not contain partially positive hydrogens. So an acetone molecule cannot hydrogen bond with another acetone molecule. But this molecule could hydrogen bond with a molecule of water through its lone pairs. Let me show this. Here are 2 molecules of water where the partial positive hydrogen on the water can hydrogen bond with the lone pair on the acetone. There are 2 potential interactions here. Hydrogen bonding is an important interaction that makes water attracted to this molecule. Another one is a dipole-dipole interaction. This partially positive carbon will be attracted to the partially negative oxygen on another water molecule. Here I'm representing 2 types of interactions, a dipole-dipole interaction here and a hydrogen bonding interaction here and here. When water is attracted to a molecule, it will be soluble in water because water is attracted to it, and so it will pull the molecules inside of the water layer. Let's talk a little bit more about solubility. Here is a table with a list of substances. You may be familiar with these things. I've also listed their characteristics as far as their polarity, and I'd like you to fill in this table for whether they are soluble or insoluble in water. Based on your experience, you might be able to answer these questions simply based on the first column. But the second column should help you. Table salt is ionic, and that means it's very polar. Ionic character is an extreme form of polarity. And from experience, I hope that you know that table salt is soluble in water. Sugar is also polar, and I'm sure you've seen sugar dissolve in water. Vegetable oil is not soluble in water because it is nonpolar. And soap is both. It's said to be amphipathic. So that means that part of it is very polar and part of it is nonpolar. Soap is interesting. It's actually partially soluble, which means that part of it is soluble, but part of it is not soluble in water. I'm going to show you a picture of a soap molecule in a minute. But first, let's talk about the interaction between water and sodium chloride. A sodium ion is going to be attracted to the water molecule with the positive charge on the sodium with the partially negative charge on oxygen. And a chlorine ion will be attracted to the partially positive hydrogens on the water. When sodium chloride is in its solid form, the sodium positive and the chlorine negative are attracted to each other very strongly. But when they're dissolved in water, they are less attracted to each other and they're allowed to disperse. The reason is because the sodium and the chlorine are both attracted to water. Water will actually cage the sodium and the chlorine ions. It's something like this. The sodium ion will be surrounded by the partially negative oxygens of the water molecule, and likewise, the negative ion of the chlorine will be surrounded by the partial positives of the hydrogens of the water. So the water aligns itself because its partial charges are attracted to the respective ions. The interaction between the oxygen and the sodium is an ion-dipole interaction. The interaction between the hydrogens and the chlorine are both an ion dipole and a hydrogen bonding interaction. The ion dipole is stronger, and so it is more important. This is why sodium chloride or any ionic compound will dissolve in water, because water will surround the ions and allow them to be separated. So the sodium and the chlorine are now less attracted to each other than they were if they were in the solid without a cage of water around them. This caging of sodium and chlorine ions is called solvation. Now let's look at some examples. In order to determine if something is soluble in water or not, you simply have to determine whether it is polar or nonpolar. In acetone, it's easy to see that this is a polar molecule, and therefore it will be soluble in water. In fact, we saw this example earlier in the presentation. Ethanol has both a polar head group and a small nonpolar part. In general, if the small nonpolar part is less than 4 carbons long, you can assume that the polar part is more important, and you can classify this as polar. The alcohol functional group can also hydrogen bond to water, and so this will be soluble. Here is an ionic compound. An ionic compound is very polar, and so this will be soluble. Cyclohexane is a nonpolar molecule, therefore it will not be soluble in water. And octanol is similar to ethanol, except in ethanol there's only a 2-carbon chain on the alcohol, and in octanol there's an 8-carbon chain on the alcohol. This is very important. Anytime the chain like this, or the nonpolar part of a molecule, is more than 4 carbons long, even if there's a polar head group on it, it's worth noting that there is a nonpolar part that will be significant. Octanol is like soap. It has both nonpolar and polar parts. The polar hydrogen bonding alcohol will be attracted to water and will be soluble in water, but the nonpolar tail here will not be attracted to water and will not be soluble. A molecule like this that has a significant nonpolar part and a significant polar or hydrogen bonding group is called an amphipathic molecule. It possesses characteristics of both polar and nonpolar. These things have special partial solubility. One end is soluble and the other end isn't soluble, and they make really interesting structures when they interact with water. Let's talk about soap. Soap is actually made of fatty acids or something very similar. We've seen fatty acids before in a previous activity. A fatty acid has a long hydrocarbon tail and it has a polar carboxylic acid head group. In this structure, I have not shown a carboxylic acid. Rather, I have shown a carboxylate. A carboxylate is just a carboxylic acid who's lost its proton. And so now I have an extra electron on this oxygen, and it's violating one of the common bonding schemes. That's why it has a negative charge. So this is a carboxylate functional group attached to a hydrocarbon tail. It's a fatty acid. A lot of the times, fatty acids are represented with cartoons that look like this. In your activity, please label the part of both of these representations that corresponds to the nonpolar or fatty part of the fatty acid or the soap molecule. This is the fatty part of a fatty acid. It's the nonpolar part, and it is not going to interact well with water. It's not going to be soluble in water. On the other hand, on this end here, we have something else, a polar and ionic group. This polar ionic group is going to interact strongly with water, and it's represented on this cartoon by the circle. I put a little negative charge here to remind myself that it's ionic and will interact with water with ion dipole interactions. This is one way that fatty acids are represented. Know that when you see this, the circle means that this is a charged or at least a very polar head group, and it's often referred to as the head. And the long hydrocarbon tail, or the squiggle here, is a hydrophobic or a hydrocarbon tail which is not soluble in water. I'm going to represent these on my next slide as triangles. When one of these types of molecules interacts with water, its head group will be soluble in water, but its tail will not be soluble. And so the water will prefer to interact with the head group, but not with the tail. Here's a little cartoon to show you what happens when you dissolve soap in water. Here is my head group, which is ionic, and it will interact with water through ion dipole interactions. And the hydrocarbon tail is not going to be attracted to water. When you put a lot of molecules like this in with water, what happens is they align themselves to form something like a little bubble, where all of the head groups are facing the water and all of the hydrocarbon tails are forced in towards the center of this kind of bubble thing so that they're not interacting with water. So on the outside of this shape is a water solution or a polar environment, and on the inside is a nonpolar environment full of hydrocarbon tails. This is called a micelle. This is an important structure, and it explains how soap works. Remember that these little fatty acids are essentially the same as soap molecules. Dirt and grease are normally nonpolar substances, and they don't dissolve in water. But when you add soap, they can be solubilized in water because the nonpolar parts can be trapped in these little micelles. And therefore, it can lift the grease out of your shirt or off of a pan, and it can carry it away into the solution. This is the structure that forms when you put soap in water. It's called a micelle. And this is the type of thing that forms with an amphipathic molecule. There's another structure that we'll learn later in the semester called a bilayer. This is a micelle, and it specifically forms with fatty acids. Chemists make drugs either soluble or not soluble in water, depending on what the drug is. Usually, drugs are large molecules. Here are 3 examples. Notice that all of these molecules contain hydrocarbon parts, and most of them have more than 4 carbons in their hydrocarbon part, and so their nonpolar properties would prevent them from being completely soluble in water. If a chemist wants to make a drug soluble in water, they can introduce ionic charges to the molecule, and it will increase its water solubility. Of the 3 examples that are shown, only one of them has good solubility in water, whereas the other 2 have poor solubility in water. It's important that this drug, an antihypertensive or a blood pressure medication, is soluble in water or in the blood, and therefore it has 2 positive charges evenly distributed on the molecule to help its water solubility. On the other hand, these 2 drugs do not need to be quite as soluble in water because they are administered in a different way, and they must pass an important part of the body called the blood-brain barrier to get into the nervous system. These have poor water solubility because they're mostly hydrocarbons. Despite the fact that they have some polar bonds, their non-polar part dominates their properties. Both of these molecules are less soluble in water, and they would be more soluble in fat. These are called fat-soluble drugs, and this is called a water-soluble drug. For small molecules, hydrogen bonding is one of the most important things if they don't have charges or ionic charges. I'd like you to rank these 4 molecules in decreasing water solubility. Pause the video now and do this. All right, I have 3 different types of things here. I have alcohols, an ether functional group, and a hydrocarbon. The hydrocarbon will be the least soluble in water because it's nonpolar. On the other hand, the group with the 2 alcohols will be the most soluble. It has the most polarity, and it also has the most potential for hydrogen bonding. This molecule could hydrogen bond 6 times with water. This one could hydrogen bond with 3 water molecules, and this one with only 2. So I could label these as number 1 being the most soluble and number 4 being the least soluble. Since this one can make more hydrogen bonding interactions than this one, this would be the second most soluble, and this would be the third most soluble. Thanks for watching this video on attractive forces and solubility. Please make sure you complete the activity, and if you found this video helpful, let me know by giving me a vote.